good evening, everyone. Welcome to Datature Park TDPK TALK Tech Highlight Episode 9. Okay, today the topic will be understanding machine learning operation for computer vision pipelines with Datature. Okay, so today the talk will cover machine learning operation and shift from model-centric AI development to a data-centric approach in the context of computer vision. Additionally, we will cover some real-life use cases of computer vision applications and some of the pitfalls encountered along the way. Finally, we will run through a quick demo of Datature platform and show you how you can create high-performance computer vision model for your projects. Okay, now I would like to welcome Mr. Kishan, our CEO and co-founder from Datature. Okay, hi.
Hi everyone. Thank you for tuning in today. Yeah, thank you for the introduction as well.
Okay, yeah. So I'll give you the stage now, okay?
Yeah, well, thank you everyone for tuning in today. I know it's about 6:30 in Thailand, and wherever you are, thank you so much for joining us. My name is Kichin. I run Datature. Datature, in a summary, is we're an AI company. We focus a lot on helping companies get to the right places where they need to be for the development team, where they need to be to build robust computer vision models. Just a bit of background about myself so that we can answer some of your questions. Datature. Before Datature, I was working as a machine learning engineer at a drone company. Then I went on to be at Rolls-Royce before starting this company. And I've seen so many different cases, where machine learning development was slow, computer vision development was slow. And if this is something that resonates with you, or you're just in general interested in what MLOps or computer vision can do for you or your company, stay tuned and I will start with the slides. So just give me a minute. Okay, so let's dive into it. So, hey everyone, today's talk, as properly presented, it's MLOps for computer vision pipelines. So in this talk, we're going to really cover a few key things and make sure that, and I want to ensure that you guys have a few key takeaways. So let's take a look at the summary. So when we start the talk, we'll be talking a bit about what computer vision is, just briefly touching upon it. What the current ML development process is, the challenges, I've learned or other folks have learned on our team of deploying ML, challenges of updating these models, the client processes, some use cases, which I'm very sure everyone will be very interested, and a bit more about Datature. And I would love to open up and end the whole thing with answering questions. So let's dive into it. So what really is computer vision? So, as defined in, a Stanford CS131 lecture, computer vision is building algorithms that can understand the content of images and use it for other applications. So looking at some of these select images we have on the right, we can easily see that, computer vision touches different facets of our life, from monitoring security, from identifying whether a certain blood scan contains cancerous cells, to monitoring construction sites, productivity, and as well as many of these other things that we can unlock with computer vision. But why is computer vision hard? You hear people saying that, diving into computer vision or machine learning itself is kind of like not an easy feat, right? Because if you look at this photo here of what people like us usually see, like, a person picture in a grayscale format, what a computer really sees isn't any of this. It's kind of like numerical representations on the right, and the computer is kind of have to understand through algorithms and modeling on what exactly it's looking at, right? And this itself, it's what's hard about it. And translating images to just pixel values, as we've seen, like for red, becoming 25500 on your computer on the RGB scale versus a different color, isn't as easy as we think. Changing all these things into just numbers and looking at it like the way we might do a simple Python program isn't just going to cut it. Look at this photo here, a very famous one. Are we looking at a dog or muffin? In some images, it might already confuse you. And just think about how a computer might be confused about just looking at images from pixel level. It's not going to be easy. So, but again, what's the key objective of computer vision? After understanding these little pixel values, these little numbers, whether they are dog or muffin, we really want to accomplish a few key important tasks to help us with our day-to-day lives. So with computer vision tasks, we have classification. Is this a cat? Is this a dog? Is it a muffin? The next advanced thing that we can do, of course, is where is the cat in the photo? Imagine you want to run some sort of use case where you're counting or tracking your cat in your apartment. After you have left the house, where has it went? You will definitely need to localize, by making the model draw boxes around the cat as you see it jump around your couch. That helps us bring a lot into context about where the cat has been. Next thing would definitely be object detection, whereby we are not just looking at cats, right? We're looking at our cats and friends. Maybe there's 2 cats, 1 dog, and 1 duck. So as we move forward, we also want to find out, industry recently also want to find out, what's the outline of cat? Is the cat a big one? Is the cat a small one? What's the shape? So as we move down this whole chain here, the task, the difficulty gets increasingly higher and harder. So that's the key task and challenge of building computer vision models. And remember, the model only can look at the pixel values of this data and just make this kind of judgment. So there are many applications of computer vision as introduced earlier. From the left, you see self-driving cars, understanding where pedestrians are, where other cars are, to things like all the way on the right, where you have kind of like safety use cases, whether someone's wearing a helmet, whether someone are wearing safety gloves when they enter a construction site, all the way down to medical use cases where people have done lesion detection, where we help doctors, hospitals, be able to quickly identify and screen very important diseases just based on scans alone, and more importantly, extremely fast and extremely at scale where humans cannot. So these are just a glance of the computer vision use cases that can be unlocked, if we all thought of use cases in the industry that we can apply to. So let's talk a bit about what the modern CV development process is and why this has caused many companies to take so long just to reach their first deployment. It starts off with companies having to acquire data. Imagine if you were a student and you wanted to do a computer vision project on counting cars. First of all, you would definitely need to acquire some kind of data, maybe taking a bunch of photos on the streets, right? And secondly, you will need to label this data, drawing boxes around this car. Maybe it's a Kia, maybe it's an Audi. You just want to draw boxes around it. And of course, like us, we all have to set up tools. Python, TensorFlow, PyTorch. The whole development team has to be on kind of like the same stack. And then using these tools, we slowly start AI models, run training, retraining, and updating it, especially when there's a new car model, right? Now you have to update the data. And of course, not forgetting the business value. What business value are we driving with computer vision model? Are we trying to count the number of cars so that we can determine whether the street is busy enough to install certain things, etc.? So the whole transition phase takes months upon months upon months. And it takes upwards of 18 different tools, not just machine learning tools, but tools such as deployment, cloud computing. Everything has to come together just for a nice box around a car working in real time. But here's the bigger problem I've seen while thinking about machine learning with other companies. The key part about machine learning and other tech stacks, such as your typical cloud stacks, your website, your full stack development, is that the ML code actually accounts for only 10 to 50% of the code base. Most of the things surrounding machine learning models are things around data collection, deployment, serving it to the industry, applying it to your internal company processes, automating tasks. A lot of these tools are not done in the machine learning fashion. They are still part of your typical JavaScript environment, cloud environment, your monitoring environment. Everything has to come together to wrap around your machine learning code base just for everything to work out at a business scale. This is tough because this involved having to move resources around not just your model, not just around your data, but as well as around your modeling code and much more. So a lot of times companies are not stuck in the front part, but they're stuck more on the deployment part. Most of us who have tried our hands in machine learning have known that it's possibly quite easy to train it on Jupyter notebooks, have your R&D team spin up certain demos. But what about deploying in the real world settings where failure or system failure would be affected by a wrong prediction? Things go off hand. So what do we do here? Let's take a look at an example. There's many ways that people deploy machine learning models. I've listed out 2 pretty common kinds. In this photo, in this kind of like a slide, we see that the raw footages may come in through a form of CCTV or like an AIoT device, where you have a camera, a video encoder, and then possibly like a neural network attached to it. So, this machine learning model, this neural network will itself predict, how many humans there are, looking across the street. And from here, of course, we can tell how many people were stopping by the shop. Maybe you realize that through this deployment, every lunchtime, there were many people crowding opposite the shop. That's great business value. That's good business analytics. But behind all of this isn't just an edge processing stack that you see here. You also have to have an ingestion server to receive how many people are there at any given minute. You have to have ingestion server to kind of update your fleet of devices across shopping malls, across the streets, just to know that they are all up to date on the recent models, right? It's usually a loop, as we see here. Raw footages come in, neural network predicts it, sends it to a server to process. We get nice visuals, but then R&D realize something is missing, update the model, and it repeats itself. There's a slightly modified version of this as well. Not all companies have security cameras that are computing things so well. Maybe you just bought a new set of CCTVs. Maybe your team just installed a bunch of cameras, or maybe you're just a hobbyist with a web camera just trying to track where your cat is at home. So what do you do then? Compared to the previous example to this example, we realized that in recent times, we can also shift the AI model into the cloud, where all your system have to do is just to send this CCTV feed back into the servers, and where frame on frame, the cloud can compute the frames for you. Both of these are pretty common in various enterprise setup as well as small team setup. This is not the fundamental issue. But the key issue is here. Looking at this data on the left, we see that it's a nice peaceful street with a shopping mall across and everyone's just walking happily. What if it comes to winter? What if it's raining? What if it's of a different condition, or where people are standing in front of camera or smudging it? Then this changes, right? Because the output could no longer be easily represented because the conditions and the underlying colors. Remember, machine learning model looks at images from the pixel value. With the snow, the pixel value changes. So how do we do about it? So this is a common example of data drift. So let's explain data drift with a real life example of what really happened. So let's take a moment to pause on the street analysis. And let's take a look at a new case where if you are a factory and you are deploying machine learning solutions, and you want to use computer vision to monitor various inspection processes, and you have the picture in the middle. This is a welding defect. And then you tell a neural network, say, hey, remember this pixel value, this label, put together is a defect. Sure, that works out pretty well. And given enough data, as we see, the model is able to do it. And the manager is happy. The manager gets a report of whatever is happening. However, everyone's happy with the system until one day, this particular factory changes its light from yellow lamps to white lamps. Just changing a simple light above your head, above the factory floor itself, to a different hue, shows the following change in the data. One is a pretty much yellow data, yellow saturated colored data. And then, of course, another one is a bit more silvery. And suddenly, the model gets so confused because the underlying, again, pixel value of the picture has changed. And the model just fails to predict all the time. So this brings on a very important portion about why managing different model status, different data sets, and model versioning is extremely important. So companies have now adapted to a new process. So remember the inference stack that we're talking about. Now companies choose to version it. They will now establish a baseline performance that maybe with the certain data set that's yellow, maybe to create another one, a subversion that contains both yellow and white data. And of course, companies should be monitoring for degraded performance. If you realize that the confidence, the accuracy of your model is decreasing over time, there must be something that's changing. It's certainly not the model. It's certainly surrounding the environment of which things are being deployed. And of course, teams do not just stick with one data. Every inspection company I've seen in the manufacturing line are always adding new data. For students with different projects, you're constantly upgrading your model to accept more and more and more different classes of information. A different car, a different cat, a different defect class. All of this require you to retrain the model over and over again. How are you tracking this? How is your servers tracking this? Remember, only 10 to 50% of the code are machine learning codes. How are the other 80% of the things and system and your tech stack tracking this? This creates a huge problem, especially for teams who want to keep iterating the models. So what teams have started to do these days is that they will start tracking the different modeling version. What's their new accuracy? How is it performing in the test environment? And then they will ship it into the inference stack and then constantly changing it, making sure that it's upgraded and up to speed. So what really is MLOps? We have thrown around this term at the start of the journey. Let's explain what it is before MLOps. So a lot of times when machine learning first became a big thing, companies were thinking that it's kind of like a linear process, right? Where you have an image and you build a bunch of machine learning codes. Could be boilerplate codes, could be codes that you've gotten from Kaggle, could be codes that you have researched and tried out yourself, and then hoping that the eventuality of it is that you get an AI model. However, from the scenario we have seen earlier, with the white light, yellow light changes, the one of the street example, what if the streets start to snow? This doesn't hold true anymore. We start to see this very popular image describing what MLOps really is. It's really more of like a cycle, more like a process, more like something that you will repeat and go around and around over and over again to make sure you have the best model. Remember, data always changes. The scenario will always change as well. So what you want to do is to set up yourself and your team on the best practices where new data could come in, new models could come in, and where you can verify its performance, you can package it up so that the other 85% of the code can account for it. You can release it, configure, and most importantly, monitor it, monitoring the performance of the AI model. So that's on briefly what MLOps is. But another key term you hear about is this thing called data-centric AI. So a lot of us have moved away, remember this diagram, of images, tons of code to optimize the model. So model, that is called a model-centric approach. But what about a data-centric approach? Let's take a look. So for a while, people thought that just improving the models, finding the best model, state-of-the-art ones from Kaggle, from GitHub, from Reddit, wherever people are getting the latest news these days, would be the way to improve their performance. But I believe with certain articles published by Andrew Ng and his team, what they realized is that instead of doing that, instead of constantly getting your R&D team to find better and better models, it was almost always more worth it for the data team or R&D team to work together to find out how you can improve model performance by simply changing, improving, and updating the data. Let's orientate you to some of the pictures you're looking at here. With some of these different use cases that Andrew and his team have listed, we see that the model-centric approach kind of yield very different improvements, typically very low. But let's take a look at some data-centric approach where the data are being changed. We can see that by changing the data, we usually yield better results than just trying to simply upgrade and upgrading the model. So the data-centric approach has been recently adopted by many companies around the world. They start to take a focus on the best ways they're collecting data, whether the teams are labeling correctly, and all these other checks and processes in place, rather than just pushing for the R&D team to just deliver a better model. So there are kind of 4 key steps that we're thinking about here in this case step. First of all, we want to improve the data. If there's a new case, if there's a new factory defect, if there's a new factory lighting that's coming in, we want to have those data in place on a single platform. Next, we will want to retrain the model. We want to be able to update the model weights and make sure that the model are now looking at all of this new data. Then we want to validate it. The last thing you want is to go to production with a model that just isn't performing that well. And of course, the last thing is nobody really knows when the data will change. The best way to do it is to constantly monitor it. So a few things that we have seen companies do while we are working with them is that the companies that place emphasis on data consistency and quality, respect kind of like data modification pipelines, whether it's creating new examples, augmenting this, and as well as companies who eventually implement some sort of system to make a more efficient process around it across teams. R&D teams are now talking to the data team. The data team are now talking to the business units, and etc. Usually yield better models at the end of the day. So let's take a look at how usually a company like Datature would manage this. Most of the machine learning journey usually begins with collecting data and labeling them. Most of platforms today you see have the ability to label this data, including open source ones. But one of the things that we want is to enable different people to label data at different times. So one of the key things we built out was to allow users to all label data all at the same time, checking each other's data, setting different level of checks so that the data that comes of this process has been seen through multiple eyes before hitting a neural network. However, having multiple annotators checking each other's work, does it really help with the scenario of the white light and yellow light situation at the factory? Does it help out with the data labeling portion as well? One of the key things we wanted to do in this space is to introduce a better way to better label the data. Let's take a look. Using the power of AI, we are also able to help these annotators and labelers on the platform, all different companies, label data pretty quickly in just a few clicks. The last thing you want is to spend months and months just labeling 300-400 data sets. So all the key things we have done here, as you have seen, is that we allow users to just point and click on data, and then automatically a mask is being generated. But is a good mask enough? What about this scenario earlier, where a traditional street has now turned snowy? What about the case where a white light has now been replaced with a yellow light, or vice versa? A better label wouldn't have solved that. So what do we do here? We use this thing called augmentations. So augmentations is a way whereby we can generate different kind of data by synthetically altering its appearance. Let's take a look here. By simply selecting a few different kind of augmentations and changes, we can force the system to generate some yellow light and white light images. Let's take a look. For example, this image here, we can see that we can rotate the image just by a bit so that the model can see what's going on. For pictures like the one on the streets, we can simply change a bit of color, we can simply rotate it a bit, we can simply add a bit of rain, add a bit of snow synthetically, so that by the time it happens, the model is more prepared for it. So this takes your data set and makes some certain synthetic changes so that by the time when something is tilted just a bit, when something is just further a bit, your model will still be robust to the changes. So we call this image augmentations. Using your current data sets, your current labels, and creating just some slight variations of it in the data. So I've spoken a bit about the problems of entering MLOps. I've spoken a bit about kind of like the problems we see with companies adopting some of these practices. So what is Datature really about? And what are we doing to make sure that companies are conformant to the MLOps scene in the computer vision side of things? So Datature, simply put, is a platform to help teams get on the best practices using AI labeling, as you've seen, synthetic image generation by creating these little changes in the data, cloud orchestration, and of course APIs. And I'll get to why APIs are very important when it comes to versioning your models. So remember this diagram we had earlier. We start from the data acquisition, labeling, and all the way to the end. What Datature does for different teams is that we try to segment out the labeling of the data and bring users all the way to integrating their business. And most importantly, we help them have the little loops in the middle so that they can iterate. So we use a single end-to-end operation where we help users manage their data labels, deploy, work with their team at the same time, all in a singular platform. Remember the IntelliBrush earlier? One thing I forgot to mention is that it doesn't matter what kind of data you're throwing at it. It works out of the box. Looking at the data here, it's a busy street on Singapore. You just need to click on where you want. The grass, the humans, this little defect here, or factory scans. It doesn't matter what it's looking at. You can simply tune it, and then once you click on it, the model will already begin guessing where the outline is, where the defect is. Is this a plant? Is that a cat? Is this a red blood cell? It doesn't matter what it's looking at. We have built an AI model so huge that it's able to recognize some of these things in just 3 to 4 clicks. Companies have been able to label 2,000-3,000 data in just less than a month with this tool. So let's move forward. One of the other things I've seen in the industry is that a lot of times the CIOs, the CTOs, the head of engineering, or even the full stack developers who were building out these previous processes, remember 80% of the code built by the full stack people, the backend people, the scientists, are usually left out of the AI process. And it's not because they are not qualified to comment on certain things. They are ultimately the one collecting the data and building the infrastructure. But what they are missing out is on machine learning skills. It still takes teams and individuals more than 6 months to familiarize themselves with 7 to 8 of the most common tools used today. So one thing we have done is that we have built all these things and condensed them into blocks. So by dragging and connecting different blocks, something as simple as this, or something as complex as 8 to 10 different blocks, will in the backend create more than 10,000 lines of Python TensorFlow code ready to train your AI models. All you need to do is to design the experiment that you want. We are not taking away that from you. You are ultimately the best person to know what kind of data augmentation is required, what kind of models you want. Is it YOLO? Is it mass RCNN? Is it UNet? It's all up to you. We just provide the blocks. And most importantly, when it comes to various monitoring stuff, it's all about having the graphs, right? Having the graphs to be able to monitor whether something is performing well, all the metrics that you want. These are usually kept and stored and reviewed whenever we deploy AI models. And remember, when I talk about monitoring model improvements, teams don't usually just train one model at any point of time. They usually train multiple models at multiple times with multiple data sets. One of the things we want to do is to provide a very intuitive way for people to figure out whether the model has been improving. If your team or yourself start taking all the AI experiments you have done and condense it to a graph, you actually can see what kind of hyperparameters matter, whether the new addition to the data set helps, whether the latest data that comes from the factory or the manufacturing plants added into your system actually improve its performance. It's all in plain view whenever you have tracked every single experiment and draw a simple line across it, like the one we see here. And most importantly, on model versioning. Most teams are swapping out files, sending files to each other through Dropboxes, Google Drive, and sometimes even Slack. It's so hard to keep track of what model is better than the others at any point of time. What everyone needs minimally is a way to trace how each experiments have been working for the past few months of experimentations. And at Datature, we help you rank all of this either by the accuracy, by validation scores, even just by time, so you know the order of things. And of course, most importantly, and as I was talking about APIs, one of the ways to provide abstraction for your team, especially when your code base accounts for 10 to 50% of the stack, is to expose an API to the team so that engineers can go ahead and integrate your AI model into any language that supports REST APIs. It could be R, it could be Python, it could even be C++. It doesn't even matter these days. As long as you're able to send an image to a highly secure API, and in less than 1 second, get back a response, you realize you do not have to buy GPUs, you don't have to buy certain specified hardware just to run super advanced, resource-heavy machine learning models. Most things are shifted to the clouds and virtualized these days anyway. The biggest thing here is that the teams just need to provide 2-3 lines of code into their code base, and they all suddenly have machine learning capabilities. And if one of our clients, where they own a manufacturing plant, most of these machines are running on 8 to 10-year-old Windows embedded systems. There wasn't any way they were able to integrate AI into these machines, making a smart factory. But with the power of APIs and Datature, they were able to just add 2-3 lines of code into their embedded system using C#, and suddenly the machines were using predictions hosted on our cloud, and now it became a smarter factory. And of course, a lot of these things we do, we try to open source it as well, contributing back to the community. Remember, we talk about actually validating the model. A lot of times people validate models in a team just by capturing a screenshot, testing on 1-2 images, and then saying that that's done. We do not believe so. We believe that if you have a video, you have a CCTV feed, it's always best to run it through a system like this. Check how much overlap there is. Are you double counting? Are we missing out things? What's the confidence of the model? And we provide open source tools for anyone to try it, even if you're not using Datature. It loads most of the modern AI models where you can track and trace video performance, frame by frame, picture performance, step by step, anytime. So putting together the whole process, usually companies just adopt 4 or 5 steps. Companies can upload data, label them pretty quickly, we usually collaborate then to design good machine learning pipelines. But most of the time, you can decide. You run multiple trials, tracking your experiments, tracing whether the model has been learning, and then you deploy them, testing them, all in just less than 3 weeks. So it's not about the time to first iteration anymore. It's also about what are the future processes in your company. How are new data being treated? And actually, what's more important is to have a centralized place where everyone can discuss, improve, and monitor the different results. And that's why we came up with the Datature platform. So today's the Datature platform is already supporting more than 3,600 teams across 46 different countries. You can use Datature today. You can start at whatever you want, and you can build any of these use cases you have seen on the screen and more. Let's dive a bit about some of these use cases we are helping enable in Thailand itself. One of the natives and of course, people over at TDPK, Central Vision. We met Central Vision just a while ago when I visited Thailand at TDPK, wonderful place. And we met founder of Central Vision, who does super amazing work with UAVs, using aerial UAVs to monitor and trace facade inspections for Thailand real estate developers, making sure that these buildings are kept up to speed, up to standards, all the cracks are being detected. Would you rather send someone climbing with a harness all the way up 20, 30 floors, or would you send a drone using the power of AI, capture these images, run them through an AI algorithm, and then detect where is it? Central Vision does that. And Central Vision does that together with Datature, where we provide Central Vision the ability to train multiple models for multiple real estate developers, multiple different kind of buildings. And together, we are able to bring a lot of value to many people in Thailand as well. Many of these use cases, many of your use cases can be solved with computer vision. So let's take a look at some of this, just for sharing some of these use cases. We support UAV tracking on the right, where we try to see whether UAV are entering certain airspaces. On the left, we can see whether from satellite imagery, where there might be roads, where there might be trees. And of course, industry use cases. One of my favorite things to use AI is to use AI for good. On the left, we see that we are able to monitor construction activity, whether people are wearing safety vests, safety helmet, before they enter a very dangerous working site. On the right is an example that I've shown earlier, where you can count the number of people outside your shop. Whether it's attracting people, it could be installed at a shopping mall, it can be installed anywhere just by tracing people. And of course, one of the use cases that I always like discussing is around medical. Today, there's not enough machine learning engineers or talents in the medical space. A lot of things in hospitals, especially in radiography and therapeutics, are still done very manually. I think we can move this faster if people out there are thinking of use cases that might involve computer vision, such as detecting cancer cells, detecting lesions in your lung scans. All of this can be enabled by computer vision. Remember, all of these use cases, while might seem very different to us, a building, a cat, a brain cell scan, ultimately these are just pixel values, numbers behind the image that the model would just have to learn. So all of these use cases are all possible on the Datature platform. And just scrolling through some of the quick ones, food packaging, we have done it. Again, these are just things that we can label and enable smarter factories, counting apples, making sure that things are consistent. Datature for construction, working with Rolls-Royce, Taikisha, to ensure that things are well and safe. Agriculture use cases where we check farms, fruits, producers on whether they are up to standards, whether they look healthy, whether there's enough space, all the way to what Central Vision is building, facade inspection, area planning even for solar plant transitions for property developers, and urban planning. And of course, finally, retail, checking how many people are in your shopping mall, whether it's proper inventory management. They're all just simple use cases unlockable by computer vision. So what does Datature really do? So apart from the product that helps you and your team train it, we have a few open source kind of activities as well. Portal is one of the ways that teams can easily check out the model performance. And Visors is a product that we have recently pushed out to help enterprise build custom dashboards, custom processes, as well as integrate better with current business processes and APIs. Could be SAP, could be this bookkeeping software they have that you want to use certain computer vision to change. We do all of that through an ecosystem of apps that are connected to each other. So this is kind of like the end of the portion. Anyone can think of many different computer vision use cases, the data that they could have collected, but you can build your best computer vision model today on Datature.io. You can get started for free, or you can just look at some of the reference materials and use cases to see how they might help you build some of these things to support your team's aspirations. And as for the enterprise people, but who might be tuning in from TDPK or Facebook and other streams, James, who's recently joined us on Datature, has 10 years of experience doing cloud and as well as engineering at Google. So he is now helping us with enterprise partnerships. And the last time when we went on TDPK, we were so honored to be able to speak to many big companies like CP Foods and Sensiri and much more. So this, if you have an enterprise use case that you'd like to discuss with us and for us to learn more about, feel free to approach James or myself if you want to know more about the platform, the developer system, and much more. So to that, I can end my presentation. I hope everyone's learned a bit about what computer vision is, the problems today, and what are the existing tools out there to solve it. And yeah, feel free to shoot any questions you have, and I hope to answer them timely.
Okay, thank you very much, Neha. I think seems like nobody's having any questions so far. So I would like to, on behalf of TDPK Digital Park, would like to say thank you very much for the session today. It's very knowledgeable. And if you have like if anyone would like to follow us, so please feel free to follow us in the TDPK Facebook Live. We will be having this kind of event eventually, like every week. So stay tuned. Okay. Thank you very much, Kun Shane. Thank you very much for listening as well. Thank you. สวัสดีค่ะ